5 factors of soil formation and parent material. There's the climate, there is the topography, you have the biology of the system, and you also have time. So the idea of the exercise today really is to have a look at the soils along the classic Catena sequence in North Wales, which runs right from the coast here all the way up to the mountain tops. And essentially the Catena sequence is an altitudinal sequence of soils which, basically as you go up in altitude you have changes in climate but also changes in geology. So now we've come to the third site on the Catena sequence. We started off at the coast and we're now starting to head up the hill slope that you can see behind us. And this is a classic, what we call foot slope position. So the main hill slope is here, and here we're coming to the flatland. And what we're going to do is we're going to have a look at the soil profile here, and hopefully we'll see some of the diagnostic features that we've seen down below, but we'll also see some things that are, very different. So here we go. So here we are, taking some of the soil out. You can see that it's a classic grassland, agricultural site, generally used for sheep production. But one of the classic things that we can see here, just a diagnostic feature before we even start to dig the hole, is that we can see that the vegetation is slightly different. We can see that, there's things like juncus here, which is a classic indicator of, high moisture content within the soil. So we almost know that we're going to find a waterlogged soil when we dig down. So as we're digging here, we can see, oh, it's a heavy piece of soil there. We can see that classically, in this foot slope position, we've got a high moisture content. And sometimes, when we've been here in the winter, the water table is right at the top. But one of the other things that you can see about this soil is the diagnostic colour. So you can see, for example, that this has got a very grey colour underneath. It almost lacks that vibrancy that we've seen, particularly at the last Alfisol site that we saw. So we dig down a bit further, and what you can see compared to the last site is that this is a very easy site to dig. We can see it's coming out, it's in grey sheets, and there's not many stones at all. So immediately that tells us that we're on a different parent material. We've not got glacial till or glacial outwash in its classical sense, but what we have here is actually a different type of glacial deposit. We have what is classically would feature in a glacial landscape of the remnants of a glacial lake. And there's no stones here. And what's happened is in the glacial period, we think that this material, this fine material that was eroded from the glacier, where you get these moraines, that basically piles of rocks that stop the water flowing out, you get lakes forming behind those, and all of the fine material that's ground out of the glacier basically sediments out in this lake material, and that's what we have here. Clearly we weren't here 10,000 years ago to know for sure, but all of the evidence of going to places in the Arctic Circle now, to Spitsbergen, Svalbard, etc., you can see these classic features there. So by analogy, that's what we are pretty convinced it is. As we dig down further, we can see that the colour is not really changing. We're still in this a very light grey colour, and as time progresses and we carry on digging the hole, we can see that the groundwater is actually rising up to the surface. So this is a classic Alfisol, but it has this waterlogged tendencies, which gives it the name. It's still an Alfisol. It's what we would call an Aqualf in the great soil orders of the world. So in the British classification, we'd call this a glade soil, a groundwater gley, where the groundwater is moving up. And you can see this classic, what we would call mottling colour. So we can see some grey here, which is the anaerobic soil where there's no oxygen, and the microbes that live in the soil have basically used all the oxygen up, and when they run out of oxygen, they use iron 3+ as a terminal electron acceptor in the place of oxygen, and then they reduce that to iron 2+ to dump their electrons from respiration, and that makes converts it from iron 3+, which is orange, to iron 2+, which is grey colour. And that's what gives it this classic colour, is that we have no organic matter really in this soil, and all of the iron has been largely reduced. And where we do have bits of iron here, in this classic feature, is actually normally associated with root channels, where roots have gone down into the subsoil and they've actually pumped out oxygen into the soil and caused this iron oxidation, this rusting of the soil at depth really. And that's the way that roots survive in this anaerobic environment, is that they use oxygen pumping to basically put oxygen deep into the subsoil to allow them to survive. If we just cut back some of this soil here, the question is, can we see any horizons here? So let's just take this bit out here, and I've not made a great job of this here, but what we can see here is that we have an organic matter rich horizon here, and then we head into, which is the topsoil, and then we head into the subsoil here with this grey coloration. You might say that we're in a flat location, but it's the topography of the surroundings that really give it its pedogenic features, and that is this hill slope that lies behind us. So it rains and the water is washing down the hill slope and it accumulates in this area. And because we've got this glacial lake deposit of this very fine material, which contains a lot of silt and a lot of clay material, it basically doesn't transmit water very quickly through it. So the water tends to back up here, and we have a lot of water accumulating at depth. It accumulates, and basically you get a rising and falling water table here. We have a nice vegetation at the surface here. It's pretty productive in terms of agriculture, but what it is doing is driving the earthworms that exist in this soil. So there's not many earthworms at depth. They can't survive the anaerobic conditions. So topography is critical, the time is 10,000 years, the biology is having a real impact, and the climate here is not particularly the climate at this site that's the driving force, it's the climate in the background here where we have all this rainfall that ultimately ends up waterlogging this soil and causing this rising and falling water table. So first of all, we've got our theta probe here. In go the prongs, and take a reading from here, from the theta probe. And interestingly, it's given a really high value, which is 76.5% volumetric water. And some people might think that's, how can you get that? That's not a normal value. But actually, if you take this soil back to the lab and you put it into the oven, it shrinks incredibly. So actually, most of this soil is actually water with, a moderate amount of mineral material within it. And we can feel that when we're standing on the soil, you can feel it's like a massive sponge. So it doesn't surprise me, but it does give us an indication of the water content of the soil, and it tells us that this is an anaerobic soil. Hence, why it has this classic grey colour to it. So the microorganisms and the roots that live in the soil use up all the oxygen, and then they go to use other what we call terminal electron acceptors to use the electrons that are produced in respiration, and they convert the iron 3+, which is the rust colour orange, into this grey colour of iron 2+. So after measuring the moisture content of the soil, the next thing that we would normally measure is the pH. So this is one that we prepared earlier, as we've had in the previous soil sites. Take the top off, and we have the pH meter just by my side here. So we put the electrode in, move it around a bit just to let it equilibrate, and then we can measure the pH on this handheld pH meter here. And the pH at the moment is 6.22 on the pH meter, and this is perfect pH for agricultural production. So Again, the university farm where we're located today at Abergwyn has added some lime to this soil to raise the pH to try and improve grass productivity to promote sheep production. Then the next thing that we can test using the same distilled water extract is the salt content. So we would expect here, looking at the hillside behind us, we know that we're getting lots of water washing down to this lowland area. So when we put the salinity probe in here, the electrical conductivity is about 0.25 millisiemens per centimetre, or 250 microsiemens per centimetre. And what that's telling us is that clearly we don't have a lot of salt here, but we have a really good nutrient content, and that is a classic feature of these sites in the lower slope positions, is that they're washing all of the nutrients from the top of the hill, and they're all collecting in this lower slope regions, which means that one of the great things about this particular Alfisol here is that it's nutrient rich because it's getting all of the nutrients from the upslope regions that are leaching out. The downside, of course, is that it's waterlogged for a large proportion of the year. So one of the things that is quite useful to do when we're in the field is also to get a handle on the amount of sand, silt and clay that are in the soil. And the reason that we want to know that is because we know that sand makes the soil freely draining. We know that clay has got a high cation exchange capacity and tends to hold nutrients in the system. And we know that silt, the intermediate bits, so we've got the coarse material, the sand, in the middle the silt, and then we've got the really fine material, the clay particles, less than 2 microns. The silt material doesn't really have much purpose at all, apart from just helping the soil form. So what we do is we get some soil, and generally you wet it up, and then you can, it's a bit like going to kindergarten or something, you can make some mud pies and things, but this is actually one of the best ways to see sand, silt, clay content. And what we do is essentially whether you can roll it into a ball. Tells us that we've got quite a cohesive structure here, so it's hanging together, so we've got a good amount of sand, silt and clay. And one of the key things is that tells us that we have quite a lot of silt here. We can rub it between our fingers and you can feel the individual sand grains there, so we know we've got about maybe 10% sand. The question is, can we feel that soapy texture that's characteristic of a silty soil? And just imagine, washing up liquid on your hands or soap, and that's what it feels like. And there is a good amount of soap in this soil, so feels like soap, so it tells us we've got silt. The key question now is, do we have any clay? And one of the classic ways of doing this, it seems quite simple in many ways, but is a classic scientific approach to measuring soil texture, is to see whether we can roll a worm. And so it's rolling quite well. The question is, can we make that into a circle? If we can make this form a circle, that would tell us that this is a clay soil. If we can't, it tells us that it's dominated by silt. So here we go. Let's roll the worm. That's not bad. It tells us we've got sand, silt and clay there, because you can feel the sand, and this is sand. And basically it won't form a circle, so it won't form a nice tight circle without breaking. And that tells us essentially that we don't have a high clay content here. We're dominated by silt, it fits with these types of lacustrine post-glacial lakes where they're dominated by this silt material. The clay flows out to the ocean and the sand gets left up the hill, and the silt sediments out in the lake deposits. And this is a classic, again, it indicates that this is a post-glacial lake environment. So soil texture, it's a really easy thing to do. All you need is your hands.